they want you to take this graph and show that it is monotonically decreasing in this domain. X is greater than -1, okay? So your first challenge is to remember what on earth does monotonically decreasing mean, right? So your clue is from the mono which means 1. So monotonically decreasing means one tone, so monotone means you're always doing the same thing, right? So always decreasing. It's always going down, okay? So if you want to show that something's always going down, apart from graphing it, which you could do, but it wouldn't be a sufficient proof for this kind of question, you need to go to calculus. That's why we've been learning it, right? Okay, so this, it's written as a fraction at the moment, which is kind of gross. So let me rewrite it like this. So you can see this is a chain rule to differentiate it, okay? Let's work out d1 dx. Let's work out the gradient function. What do I do? Okay, so let's do the outside first. So bring the power down, okay? Then reduce the power by 1, which is -4. Watch out, okay? And then what? That was the outside. What's the rest of chain rule? The inside, which in this case the derivative of the inside function is just 1. So actually I'm done, okay? So just to put that in a more, what we're normally used to, that -4, right, that power, doesn't apply to this number. It only applies to that function, okay? So you've got -3 on x plus 1 to the power of 4, okay? So there's our derivative. Now if we want it to be monotonically decreasing, what I want to show is this thing is always negative in the domain that I'm interested in. Does that make sense? This thing is always negative in the domain. How do you go about doing that? Now, the first instinct is to sub some points in, okay? Now that's fine to verify that you're correct, okay? Because you can put some in and you're like, oh yeah, sure enough, anything you put in this domain, it'll be negative. You're happy, right? In fact, anything you put in even to the left of this domain is also, okay? Now, we're going to get at that in a second, why that's important. But just subbing in points is not enough. Is not enough. We've talked about this before, right? Like in maths, or in life, there are multiple methods of proof, some better than others, some valid and some not valid, right? So what you're trying to do is proof by example. Why doesn't it work? Why isn't proof by example a valid method? Prove yourself.
Why is it? Why isn't it?
Why isn't it? Why can't I just say, for instance, take like 5 points, or 10 points, or 50 points, show they've all got negative gradient, and say, well, I can go home and I'm happy. Yeah. That's right. I want to prove for all of them, right? This inequality represents an infinite number of numbers, okay? So 5, 50, 5 million won't be enough. Okay, so I've got to do something else. I've got to employ some logic, okay? So, what am I going to do? I want to look at this thing down here, the 4, okay? The 4 turns out to be critical, okay? Another way of writing is, it's something to the power of 2 to the power of 2, okay? So it's a square, really, is what I'm interested in, okay? Now, why would that be significant? Why is it important that it's a square? Yeah. Say it again. Yes, it is an even function. However, that's... You can get even functions, which will be negative as well. Okay, so the evenness influences. Okay, that's what we're getting at, right? So not only is a square function even, okay, it's going to have that kind of symmetry, but it's always going to be positive, right? Whatever numbers you throw in there, with the exception of -1, you're going to get a positive number. Okay. So here is what I would say. I would say x plus 1, or well, actually, where should we start? I'm going to say that this is greater than or equal to, greater than 0 for x is greater than -1. Are you happy with that statement? Because it's a square, right? Now, by the way, I have to say this because otherwise, if I put -1 in, I get 0, which is not positive. Okay, it's not anything. It's a bit weird, a bit below number. Yeah.
You have to say that's true because it's a square.
No, that's self-evidently true. Okay. In fact, by the way, we'll go into this in more detail in a topic called inequalities, which has inequalities. Okay, but this is something you guys know. Squares are positive. Okay. All right. Now, therefore, I can go from here to this line over here. Now, what do? I'm going to take the reciprocal of both sides. Okay. Now be careful here. The reciprocal of this, it's not 1 over 0, right? In this case, I'm saying, well, if I've got something positive, if you take 1 and you divide it by a positive number, you're still going to get a positive number, right? So the inequality still holds. You happy with that? Now to get to what I'm actually interested in, I'm going to multiply by minus 3. And you guys know when you multiply both sides of an inequality by a negative number, what happens? The sign changes direction, okay? So that's why I'll get minus 3 over that. That is negative, as I'm interested in, okay? So therefore, dy on dx is less than 0 for the given domain. Sorry, other way around. And so your conclusion is, therefore, it's monotonically decreasing. Yeah, question?
If you graph dy on dx against x, and like you said after that it's going low, is that proving it because
Okay.
it doesn't exactly show that it's not going to cross the
Okay. I think you probably you might be able to get rid of that. I think this is, what, 2 marks? 2 marks?
Yeah.
Is it 3?
Yeah, 2.
Is it 2? I think you probably could get away with that because if you're provided number 1, your graph is good, and number 2, you've differentiated properly. Okay, because really what we're looking at is for you to get to the derivative and get that monotonically increasing or decreasing. It's a property of the gradient function. Okay, so that's sort of where your main work is. And whether you do it algebraically or graphically, I don't think it matters too much. Okay.
I just thought that would be a given. That's why.
Which part?
The bottom is always positive. That's why it would be negative.
Oh yeah. Okay. So this is it's just a more rigorous way of saying it.
Yeah,
So
when I
can,
lose marks,
can you just take the negative out and say that since a constant doesn't change the concavity of the function?
Yeah, you can say it, but it's always us mathematicians. We don't like words, right? So the strength of your argument starts to degrade a little bit when you just have the equations. Like looking at this is you don't need to argue it. It stands for itself. Does that make sense? So,